everyone. It's your favorite chemist again, Adrenaline, the Bazooka Prophet. Today, we are going to be talking deeply on, I'm going to be teaching you on a new concept under chemical equilibrium, talking about what we call the equilibrium constant. Now, very simple. Now, we should understand that the equilibrium constant is represented with the symbol, which is KQ, which is equilibrium constant. And in chemical equilibrium, there are two categories. We have the Kc, which is the concentration equilibrium constant, and the partial pressure equilibrium was constant. Very simple. Now, we should understand that the equilibrium constant was first instituted or was first expressed by two Norwegian scientists, and they were Carter Goldberg and Peter Waj in the year 1864. Now we should understand that the equilibrium constant is a mathematical expression of their what now of their of their active of their law of active masses, or the law of mass action. Now, in the law of mass action, it simply states that at constant temperature, the rate of a chemical reaction is proportional or is directly proportional to the active masses. The active value talks about the concentration of the reactive masses raised to power the stoichiometric coefficient, as you can see right here on the board. For example, the KEQ of this given reaction right here on the board. Remember, we have said that a chemical equilibrium constant is the rate of the forward, over the rate of the backward. This is the forward, this is the backward. So if I have to write the equilibrium constant for this, it will be KEQ, which is the equilibrium constant, is equal to the rate of the forward reaction over the rate of the backward reaction. And according to the law of mass action, it means the concentration of the of the forward reaction raised to the power of the stoichiometric coefficient over the concentration of the reverse raised to power of the water, the stoichiometric coefficient, which is simple. So here become, see now, the concentration of C, and that the stoichiometric coefficient of C here is this small c you are seeing here. The product now of the D to the stoichiometric coefficient over the reverse here now, which is A, to that of the small a, that of the B to that of the what now, small b. That is how to represent an equilibrium constant for a given reaction. Please do note, it is the rate of the forward over the rate of the what now, the reverse. And take note, remember we talked about that the chemical equilibrium constant is a mathematical expression of their what now, of their law of mass action, and that the law of mass action simply states that at constant temperature, the rate of a reaction is proportional to the active masses, and the active masses are what is represented on the board as the concentration of the reacting substances over raised to power the stoichiometric what coefficient. Now we make progress. Now on the board we are given some questions, which is write extraction for Kc and Kp if applicable for the following reversible reaction at equilibrium. At equilibrium, very simple. I'm going to be teaching you a simple steps on how to address such questions. Sit back, relax, and have fun chemistry, because it is easy. Now, I've told you, in writing for equilibrium constant of a substance of reactive substances. Please take note. Do not forget this major rule. The equilibrium constant KEQ is applicable to substances in gaseous state and volatile state or aqueous state. Meaning it is not applicable to substances in their solid and liquid. No. Please, a lot of students have had issues with this single statement. You do not write equilibrium constant for substances in the solid and liquid state, or rather in the gaseous state or in a more volatile state or in the aqueous state. So this is what is necessary or needed. So we can now fall back to the question and take note. When the substances I am working on are only in their gaseous state, what do? I will make use of Kp, which is the pressure, because pressure affects gases. While C, when it now involves aqueous state, I made what we call the concentration of it. So we can solve the following questions within the twinkle of an eye. Okay, so let us see some of them. So let us solve them. So please take note, do not forget. So we take the first one, which is example 1, that Kc is equal to, remember, the forward over the rate of the forward over the rate of the backward. I come here. Now, the concentration of the hydrozonium ion, please do not take this one outside. Come on, mistake that you often make. You have to take this, no, it goes together. The concentration of the hydrozonium ion multiplied by the product of the concentration of the fluoride ion over, remember, I cannot write that of the water, because why? It is in the liquid state, so it will be omitted. We'll fall back to this hydrogen fluoride. So the concentration of the hydrogen fluoride, and that is the answer. You see it now? So it is a go. Please do take note of it. Very easy. Now we move to the next one. Now in the next one, if you observe the state of what you are seeing here, they are all in their gaseous state. You get me now? They are all in their gaseous state. So I will make use of okay, let me first of all write it for you in Kc before I turn it to become Kp. In Kc, it will be, see, the concentration of nitrogen 4 oxide raised to power, this is the coefficient now, the stoichiometric was coefficient, raised to power 2 over the NO raised to power 2 and the O2. You get me now? Now, but because it is, or the state of these reactive substances are in their gaseous state, so it will be Kp, which is Kp is that equal to, so here become, these are to represent it, P square NO2 over P square NO, then as dot P O2. That is the final one. Then we'll move to the last one. In the last one, it involves a very common reaction in organic chemistry, which is what we call the esterification process, whereby an organic acid will react with an alcohol to give out what we call an ester, which is ethyl ethanoate with water. Now remember, it will be Kc is equal to product, which is the reactant over what now? Over the reverse. I won't write for this water here because it's in the liquid state, so it will be omitted. So it will be the concentration of CH3, which is the ethyl ethanoate, over, okay, we'll put the state here, ethanol here, ethanol with that of the ethanoic acid. So, and on that very note, we come to the end of what we are having here. You see how it is? The first one, the second one, the third one. Now, in a nutshell, we've talked about the equilibrium constant. Now, in our next video, we'll be talking about strictly, or I'm going to be teaching you the relationship between the KP and the KC. For now, I remember humble self, adrenaline, the bazooka prophet. I love you guys.